Alright, so the next aspect of the water cycle is how much water is getting into the soil, and then how much water is moving through the soil, and how does it wet and dry. So we're just going to show you some simple things that we were going to get you to do, but we'll just demonstrate it for you now. So the first thing is this plastic ring, which we've hammered into the soil. We just put this over and then we can knock that into the soil, and that makes a nice sleeve into the soil. And then we can add water to the top and the water will infiltrate, so we'll get an infiltration rate. Again, if we know how much volume's gone in over time, we divide by the cross-sectional area, then that's millimeters per unit time, which is our unit for the water balance. So I'm just going to top this up with some water, and essentially that's full. So we would start the stopwatch, and then we would wait for 30 seconds, and we get our graduated cylinder, which is in milliliters, and I get that to exactly top, so I can make a measurement from it. So after say 30 seconds, I can then top this back up so it's absolutely brim full. Okay, and then I now know that that's 250 minus 120, and that's how many milliliters have gone in the unit of time. So that we can then convert that to millimeters per hour. So we often see that it's been raining a lot here, so the soil's quite wet, so the infiltration rate's a little bit lower. But in dry soil, the infiltration rate is really high. It tends to go in very quickly, and then it falls off with an exponential till it gets to its background level. So the background level is the kind of saturated infiltration rate, but before then there's kind of an infiltration capacity curve, and so we're interested in that. This has got a few errors going with it. So as the water goes in, it tends to spread laterally, so it tends to be slightly higher infiltration. Plus the weight of the water itself is driving the water in to the soil. So they're kind of errors. We can improve this slightly by having a double ring infiltration, so we can actually have an inner ring. I won't bother squeezing that in now because it make a lot of splashing. So essentially you can actually have water around the outside, which makes kind of a sleeve of water, so that you get a slightly more accurate infiltration rate through the middle ring. Okay, but that still has the problem of the head of water squeezing into the soil. But this is really great if you want to know whether your soil is high, medium or low. If it's really high, you know all your rain's going to infiltrate. If it's really low, and after a few millimeters of rain it's saturated, you know you're going to generate lots of overland flow. But the ones in the middle are the awkward ones, so this is quite an awkward soil, and so you have to have an improved method. So let me just grab a piece of kit. So we're going to look at this kit that's on the floor here, and I've got another one here. So this is an improved method. So we have our contact with the soil here, which is permeable, and it's graduated. Again, we're going to get the volume, and what we do is we can fill this with water, but now instead of having the head of water driving the water in, we can counterbalance that water by adding some water to the top here, and so when it drips, the only thing that's going is the infiltration rate of the soil. So we've actually got one set up here. I don't know whether you can come down and see it, but there it is. And so what we would have done last year, we would have made you stand for an hour measuring the infiltration rate using these two methods, and when you see the bubble, that means that water's going into the soil. Okay, so that's the infiltration. The other way we try to get a handle on what's happening in the soil is we try to look at the soil moisture. So I've got a couple of bits of kit here which are essentially the same bit of kit, in that this wire here would connect, I can get the end of it, would connect to this probe here. Okay, so if you have a quick look at this probe, this is called a capacitance probe, and basically it uses an electrical method, so it beams out some electricity over an area, and depending on how much soil water there is, there'll be a conductivity, and that is picked up by the middle prong, and therefore that can be pre-calibrated to be matched with soil moisture. So if we had a soil moisture probe like this, a handheld one, you could just walk along and you would just look at this particular soil moisture meter. It's not got a battery in at the moment, but you would just press bing, and it would give you a measurement either as a percentage or usually as a fraction of the volume occupied by water. So if it said something like 0.4, it means of 100% of the volume, 0.4 of it, 40% of it is water. And so that's quite a useful way of making lots of measurements. But we need to know what's happening inside the soil dynamically, so we often bury our probes. So here's one. It's all getting compounded up on each other. So this one, we could go into the soil, so we make a nice hole in the soil, but we don't put it in like that. We put it in at an angle, and we'd have a long discussion as to why that was, but we haven't got time now. So if the soil was here, we go in at 45 degrees, so we know what the depth is, and therefore we can log continuously through the wire, maybe every hour, what the soil moisture content is, and we can have them say at 20, 40 and 60, and then we can put that onto a logger. So we can wire this DL6 logger, so we wire that onto here and we can log everything. Now the urban observatory don't need to log, they go straight onto the web, don't you? Very high tech. But a traditional setup would be to just wire it into a logger, but you might also have a soil temperature and maybe a rain gauge. So you might have 4 of these, soil temperature and a rain gauge. So they're quite useful. This just tells you the behaviour of the soil over time. The change in soil moisture is a hugely indicative representation of how much evaporation is and what the dynamic is over time. So if you know the rain, you know the evaporative potential, and we know the soil moisture, we're really cooking with gas. So probably the only other things to know is, we want to know if there's a water table down there. Well, we can auger little holes, and we can add in observation tubes like this. So this would make an observation well. We'll do more about deeper groundwater later with Brian Thomas, where they would be called piezometers. But for the moment, if we were to put this into the ground, if there was any water table present, we do get shallow water tables building up in soils, then we could just use something we call a dipper, which is just lower down here. It's on a little measuring tape, and when it hits the water it goes beep, and then you know, beep, beep, then you know how deep the water table is. You can also cheat sometimes and just pour some water in, fill it up and see how quickly it disappears, and we call that a falling head experiment, and that really just tells us once again whether it's really high conductivity soil, medium or low. Again, it gives us a bit of knowledge. So there are some very high-tech alternatives to these which will be in the notes. So for soil moisture, we've got some buried probes that we might show you in a minute. For infiltration, we've got something called a Guelph permeameter, which is supposed to be the best way of getting the soil dynamics and soil conductivity. And we can also have slightly more high-tech versions of water tables. So if you had a borehole or a shallow